Turn text into searchable counts and simple matches. By the end, you will count corpus word frequencies, build a stable bag of words vector, run simple query matching, filter stop words, and pick the best matching document. You will see how these pieces fit into a lightweight retrieval baseline and why each step matters for speed and clarity. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Word frequencies and bag of words matter because they give you a compact, interpretable representation of text. The core property they optimize is exact overlap and explainability, which helps with fast lookup and clear diagnostics. The trade-off is context and order. You lose sentence meaning, but gain sparse vectors, lower latency, and easy indexing. At small to medium scale, this approach is fast. On hundreds of thousands of documents, the vocabulary and matrix size grow, and memory becomes a real limit. Think of bag of words as counting and aligning. First, you find which words appear and how often. Then you build a fixed list of those words, so every document maps to the same positions. This shines for keyword search, document filtering, and simple classifiers. It fails when you need syntax, negation, or deep semantics. Our goal is to keep things practical and traceable. We will build a tiny pipeline that counts words, makes a per document count vector, scores documents by simple overlap, then filters stop words and returns the single best match. First, we will tally the corpus-wide frequencies. This snippet counts corpus-wide word frequencies and prints the top 5 terms. It creates a tiny corpus in the variable docs with 3 short sentences and uses counter, which tallies items, to aggregate tokens produced by simple white space splitting. The counts variable holds the per term totals, and the code sorts terms first by descending frequency, then alphabetically to make ties deterministic. Printing the top entries shows which words dominate the corpus and how often they appear. That visible ranking helps you verify basic tokenization and confirms that repeated words like surface as the most frequent entries. Now we will build a single document vector using the shared vocabulary. This snippet turns one document into a bag of words count vector that lines up with the earlier vocabulary. It reuses the vocabulary derived from counts so the order is consistent and stable across runs. The variable D selects the first document from docs to keep the example focused and easy to read. The list vec computes how many times each vocabulary term occurs in this example document. So, each position corresponds to a particular word in the vocab list. Because the vocabulary is sorted, the vector remains interpretable and comparable across documents. The printed vector shows raw term frequencies per position, which is the core structure many downstream models and retrieval systems expect. Next, we will rank documents against a short query using set overlap. This snippet ranks documents by Jacquard similarity to a short query. Jacquard similarity measures the size of the intersection divided by the size of the union of 2 sets, so it captures unique token overlap relative to combined vocabulary. The variable Q holds the query text, and QSet converts it to a set of unique tokens. For each document, the code computes the Jacquard score between QSet and the document token set, stores those scores, and then sorts document indices by score while breaking ties by index. Rounding keeps the numbers readable. If you add more unique terms to the query, the union usually grows and scores tend to decrease. The output shows which documents best match the query by shared unique words. Now we will remove common words and see how rankings change. This snippet removes stop words and recomputes the most frequent terms to reduce noise in the counts. The set stop lists common or uninformative words that we want to ignore when counting. So the code rebuilds counts by skipping tokens that appear in stop. That operation reduces high-frequency filler terms and highlights more content-bearing words. After rebuilding the counts, the code sorts and prints the new rankings so you can compare before and after. Expanding the stop list will emphasize rarer content words but risks discarding useful signals. Shrinking the stop list preserves more detail but may leave the vocabulary dominated by common words. The printed list reveals a clearer, less noisy vocabulary. Finally, we will score documents by bag of words overlap with the filtered query. This snippet retrieves the best matching document using bag of words overlap against the filtered vocabulary. The variable terms filters the query to tokens that are present in the filtered vocabulary counts, so it applies the same stop word policy to the query. For each document, the code sums up how often those filtered query terms appear. So repeated matches add more to the score than single occurrences. The list of scores is sorted, and the code returns just the top result as a compact baseline for retrieval. Increasing the number of terms in the query generally raises scores for documents that share more words. The printed pair shows the winning document index and its overlap score. Recap: bag of words is counting and aligning words across documents. Use it for fast, interpretable matching and simple baselines. Caveat: it ignores order and deeper meaning, and vocabulary size can explode. Next step: try TF-IDF with n-grams or tune the stop word list to see how weights and query length change ranking and retrieval quality. If you want to scale, add an approximate nearest neighbor index and measure speed and accuracy trade-offs. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.